All right, welcome back. So we're gonna try example number 4. This is a very, very interesting problem. There's two approaches we can do this problem. One way is to apply direct directly the chain rule as it is right now, right? So you have to do this is the outside function, this is the inside of the logarithm, and so we would have to take the derivative of this. Um, um, so that would be 1 over all this, and then 1 over the natural log of 10 and times the derivative of this. But this, like the derivative of this, you have to use the quotient rule, right? And then you have to use the power rule for some point. So it is very, very, very messy, right? It's gonna take a lot of work. So the alternative is to think about outside the box, right? And use the fact that this is a logarithm problem, and that we have special properties of logarithms that allow us to expand this. And by expanding this will make the process way, way, way easier. So if you're watching this video, kudos for you. You're really gonna learn a very great technique. So let's begin. So let's find the derivative of this. But before we do that, what we're gonna do is we're gonna rewrite this by expanding, right? Expanding the logarithm. And that is, we're going to use those properties that we discussed earlier, and that is use the fact that because there is a division within the logarithm, that means that we can separate this into two different logarithms, right? That we can have a logarithm minus another logarithm. And often here is the numerator, and here your denominator. So what I'm saying here is we're going to take the numerator minus the logarithm of the denominator, right? Like that. That is the quotient property of the logarithm. Now, I could come back here and say, well, we have this square root, and we don't have a specific rule for square roots, but we have a rule for power rule. So what I would suggest here is in the next line is to rewrite this as a power form. So we know that square roots can be written in the form of a power of a power of 1/2. Okay, right. So this line was by the quotient property. This one was by algebra, right? Just changing a radical square root into a power 1/2. All right, and then from here, what we're gonna do is we're gonna continue with the algebra. We haven't even started taking the derivative. We're just setting it up. And then, so what we're gonna do is we're gonna use the property of powers that allows us to change the powers to the front, right? To move the powers to a factor. So that means by the power rule of the logarithms, we have 1/2 times the logarithm of 3 plus 13x to the 6 minus 8 times logarithm of x, right? And so this is now way, 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 way easier for us to do, because all we gotta do is take the derivative as of what we have, right? So we have this, and to take the derivative of y, we're gonna do y prime is equal to the derivative of the first one, right? Well, this is a constant being multiplied to a function, so we use the constant multiple rule, right? Meaning the constant carries over, and you multiply by the derivative of the function, right? So let's do that. So we have 1/2 times, what is the derivative of logarithm of 3 plus 13x to the 6? Well, according to the logarithm property, right? If you have a function inside, the derivative of this is going to be 1 over the inside function multiply by 1 over the natural log of your base, and then at the end you gotta multiply by the derivative of the inside. So this is a combination of taking the derivative of logarithm and taking and multiplying by the derivative of the inside, right? So follow this pattern. We're gonna have 1 over the inside. In this case, this, right? This is always your inside. So 3 plus 13x to the 6 times 1 over the natural log of the base. In this case, even though there's no base there, that assumption is that's always base 10. And multiply now by the derivative of the inside. I'll put this as a box. That way we can remember that this, we're going to take the derivative of this. All right, so that's the derivative of the first term. Now we're going to take the derivative of the second term. The similar argument, this is a constant multiplied to a function, so we have to use the constant multiple rule here as well. So we have 8 times the derivative log of x, so that's just going to be 1 over x times the 1 over natural log of 10. Right? All right, so that's pretty much it, right? We have found the derivative. All we gotta do is come back and take the derivative of that. In the meantime, yeah, let's just do that. So 1 half times 1 over 1 plus 13x to the 6 times this, and then the derivative of this, well, the derivative of 3 is 0, so that goes away. The derivative of this part is, we have to use power rule, so that will be 6 times 13. That's going to be 6 times 13, I believe that's 78, and then times x, and then subtract 1 from the power, so that's a 5. And then minus 8, 1 over x, times 1 over natural log of 10. All right, so that's pretty much it. We found the derivative. All we gotta do now is put everything together and simplify. We could see that 1/2 and the 78 can cancel each other out and give you 39. So therefore we have just 1 over 3 plus 13x to the 9. So multiply these two together and multiply these two together. So that'll give us minus, and then x to the 5th, right? Don't forget the x to the 5th, and don't forget the 39. So that's gonna go up here. So that's that times that times that times that gives us 39 times x to the 5th. Minus, and then do the same thing, right? This is imaginary 1 here. Multiply 8 with 1, and then 1 with x with natural log of 10. And there you go. We have found the derivative of the function, right? And let me just tell you that everything that we did was mostly just algebra. Let me tell you, from here, that was algebra, right? Everything up to here was algebra. This line was calculus, and then this line was calculus, and then from here to here was algebra, right? So there was only 2 lines that was calculus. Everything else was algebra, right? So I want to say that